At the center of a distant galaxy lies a black hole so massive it makes every other one look small. Today, we're taking a journey to Phoenix A star, a cosmic hole billions of times more massive than our Sun. What is the largest black hole humans have ever detected? The universe is full of extremes. Stars that explode with the force of billions of nuclear bombs, clouds of gas so vast they span light years, and objects so dense that not even light can escape their pull. Among these extremes are black holes, mysterious cosmic engines that warp space and time and dominate the environments around them. Some are born when massive stars collapse. Others sit at the hearts of galaxies, quietly shaping the fate of billions of stars. But even among these cosmic giants, one stands above all others, a behemoth so massive it challenges our understanding of how black holes can form, grow, and influence their surroundings. This is the story of the largest black hole humans have ever detected, not in our own galaxy, not next door, but in the vast expanse of a distant cluster of galaxies. Its name is Phoenix A, and it is far larger and more powerful than anything we have ever seen in the Milky Way. When astronomers point their telescopes toward the constellation of Phoenix, deep in the southern sky, they are not really looking at a single star or a nearby gas cloud. Instead, they are looking at one of the most massive structures in the known universe, the Phoenix cluster, a dense swarm of galaxies bound together by gravity. At the very center of this cluster lies a giant elliptical galaxy that glows with intense radiation. This glow is not from stars alone. It comes from the chaotic region around a supermassive black hole, a place where gas, dust, and even stars tumble toward an invisible boundary from which nothing can escape. As matter spirals in, it heats up and shines across the electromagnetic spectrum, from powerful X-rays to radio waves. It is this telltale energy that first drew scientists' attention, hinting at something enormous at the core of Phoenix A. To understand why Phoenix A's black hole is so remarkable, it helps to know a bit about the black holes we already have in our cosmic catalogue. In our own galaxy, the Milky Way, there is a supermassive black hole called Sagittarius A star. It weighs about 4 million times the mass of our Sun, unimaginably heavy by everyday standards, but relatively modest compared with some of the giants out there. In distant quasars, black holes have been found with tens of billions of solar masses. These quasars shine so brightly that they can outshine entire galaxies, their light reaching us across billions of years. Among these, the quasar known as TON 618 has been one of the biggest names in supermassive black hole measurements for decades, with mass estimates of around 60 billion suns. But even this titan may not hold the crown anymore. When scientists studied Phoenix A, they found evidence that its central black hole could weigh around 100 billion times the mass of the Sun or more, potentially pushing it into a category of black holes so massive it defies the expectations set by previous discoveries. We don't see individuals wandering around the galaxy carrying that much mass, but black holes don't need to look like ordinary objects. Their size isn't determined by the volume they occupy. There is no surface to see, but by the mass crammed into an incredibly small region of space. When we say Phoenix A's black hole is the largest, we mean its mass, and the size of the invisible boundary called the event horizon are both at the extreme limits of what scientists have been able to observe. Imagine for a moment a sphere around a black hole. This invisible shell is what astronomers call the event horizon, the point beyond which nothing can ever return. For Phoenix A, that sphere would stretch so wide that if we placed it at the center of our solar system, the event horizon might extend far beyond the orbit of Pluto. Light itself would struggle to escape the grip of this gravitational titan. The scale is almost impossible to visualize because it outstrips our everyday experience. But filmmakers and animators use comparisons like this for a reason, to help the audience feel the magnitude of what is being described. Phoenix A is not just big, It reshapes our sense of size and scale in the universe. This matters for science because black holes are not cosmic curiosities. They are engines that drive the evolution of galaxies. They regulate star formation, shape the motion of surrounding galaxies, and affect the distribution of matter on scales that span millions of light years. The incredibly high mass of Phoenix A's black hole puts it in a category that pushes against the limits of current theories about black hole growth. Black holes grow by eating gas and dust, by merging with other black holes, and by absorbing stars that wander too close. But every time a black hole feeds, it also pushes back. The energy released by falling matter can heat surrounding gas, creating powerful jets and winds that can slow or halt further feeding. This feedback process acts like a natural governor on growth, making it difficult for black holes to keep gaining mass indefinitely. Yet here, in Phoenix A, we may be looking at a black hole that has somehow bypassed or overcome these limits, growing to a mass that challenges astrophysicists' expectations. What makes Phoenix A even more fascinating is not just its mass, but the environment it inhabits. The Phoenix cluster is a pressure cooker of activity. It is filled with hot gas, vast streams of plasma, and hundreds of individual galaxies locked in a gravitational dance. The center of this cluster is ablaze with star formation, rates that dwarf what we see in calmer galaxies like the Milky Way. The connection between the central black hole and this wild star formation is one of the hottest questions in modern astronomy. In many galaxy centers, energy from the black hole suppresses star formation by heating surrounding gas and pushing it away. But in Phoenix A's host galaxy, star formation seems to be thriving alongside relentless feeding at the core. This coexistence strikes scientists as both surprising and illuminating, because it reveals that the relationship between black holes and their host galaxies is more complex than previously thought. To detect and estimate the mass of Phoenix A's black hole, scientists use indirect but powerful techniques. They observe the X-ray emission from hot gas falling toward the center of the galaxy, and they model how that gas behaves under the influence of gravity and extreme energy output. They also study the motion of gas and stars near the center, anything that can reveal the gravitational tug of an unseen massive object. By combining these observations with sophisticated computer simulations, researchers can infer not just that a black hole is there, but how massive it must be to explain the behavior they see. These methods are not perfect, and uncertainties remain. Measuring something as distant and massive as Phoenix A is not like measuring an object in a laboratory. It requires careful calibration, deep understanding of astrophysical processes, and the willingness to revise models as new data arrives. But even with these uncertainties, the evidence points to Phoenix A as one of the most titanic black holes ever found. Another reason Phoenix A matters is that it may redefine the upper limits of black hole math. Astronomers have proposed classes of black holes that extend beyond the supermassive category into realms called ultramassive or even stupendously large black holes. These terms are more than colourful descriptions. They represent attempts to classify black holes that sit at the upper extremes of mass and influence. Phoenix A may be a prime example of such an object, offering a natural laboratory where scientists can test ideas about how black holes evolve, how they interact with their environments, and how their growth may have shaped the early universe. If Phoenix A is truly in the uppermost category of black hole masses, it suggests that the universe has a broader range of black hole behavior than we previously understood. The search for the largest black holes is not just about record setting. It is about understanding the rules that govern the cosmos. Black holes like Phoenix A hold clues about the formation of galaxies, the flow of energy across vast cosmic distances, and the history of the universe itself, from its earliest moments to the present day. Observing and modeling these objects pushes the boundaries of technology and theory. It drives the development of ever more powerful telescopes, more sensitive detectors, and more advanced computational tools. When we study something as massive as Phoenix A's black hole, we are also studying extreme physics, the behavior of matter under gravity so intense that our current models of space and time are tested in new regimes. How did we find Phoenix A? Phoenix A discovery starts in one of Earth's most remote scientific outposts in the frozen plains of Antarctica, where a telescope unlike any other scanned the sky, not for craters or comets, but for the subtle imprints left by the larger structures in the universe. On that icy continent stands the South Pole Telescope, SPT, a 10-meter instrument designed to observe the universe at microwave wavelengths, searching for ancient clusters of galaxies by their shadows on the cosmic microwave background, the leftover glow from the Big Bang. In 2010, researchers using this telescope were surveying a vast patch of the southern sky, looking for something that would betray the presence of a massive cluster of galaxies so distant and so massive that its influence could be detected across billions of light years. What the SPT team found was remarkable. Among the dozens of galaxy clusters they catalogued, one stood out for the way it bent and shifted the microwaves passing through it. These distortions, caused by hot gas in massive clusters scattering the background radiation, an effect called the Sunyaev-Zeldovich signal, told astronomers that here was a galaxy cluster unlike most others, one so dense and energetic that it carved a noticeable imprint on the oldest light in the universe. What eventually became known as the Phoenix cluster was catalogued as SPT-CLJ2344-4243, a name that, at first glance, might seem cryptic to anyone outside the astronomy world. But for scientists, it was a clue to something extraordinary lurking at the edge of the observable universe. Once the Phoenix cluster was identified through this subtle signal in the cosmic microwave background, attention quickly turned to what was happening deep inside it. Telescopes that observe in wavelengths beyond visible light became critical tools in this investigation. Among these was the Chandra X-ray Observatory, a space telescope capable of seeing extremely energetic emissions that visible light cannot capture. When Chandra trained its sharp X-ray vision on the Phoenix cluster, it revealed something astonishing. This was not just a massive cluster of galaxies, but the most luminous X-ray cluster ever observed. The amount of X-rays pouring out of the Phoenix cluster was larger than anything seen in similar objects across the cosmos, signaling an intense level of activity at its core that no one had expected. In X-ray light, the Phoenix cluster blazed like a cosmic forge, much brighter than any other cluster in the same class. This was not a dim, distant assembly of galaxies quietly drifting through space. This was a powerhouse of energy and motion. X-rays in astronomical observations are the hallmarks of extreme environments, places where matter is heated to millions or even tens of millions of degrees, where gravity squeezes gas into a frenzy of motion that causes it to shine with extraordinary energy. In the Phoenix cluster, Chandra saw vast amounts of hot gas at temperatures far beyond what is typical for galaxy clusters, and these X-rays were coming predominantly from the cluster's core. The sheer brightness of this emission suggested that something at the heart of the Phoenix cluster was not just holding on to this gas, but shaping its flow and behavior on a massive scale. With this discovery, the scientific focus narrowed from the cluster as a whole to its central region, a place where something unimaginably powerful was at work. As scientists delved deeper into multi-wavelength data, combining X-ray results with optical and radio observations from other telescopes around the world, patterns began to emerge that would change how astronomers think about galaxy clusters. Visible light from the Hubble Space Telescope showed a bright elliptical giant of a galaxy sitting at the center of the Phoenix cluster, and radio data from the Very Large Array revealed structures that hinted at jets, streams of particles accelerated to near the speed of light, emanating from this central galaxy. And at the very heart of this galaxy was a supermassive engine, what astronomers call an active galactic nucleus, AGN, a region where immense gravitational forces are at play as matter spirals inwards, heating up and radiating energy across the electromagnetic spectrum as it does so. This AGN, identified with the central galaxy later named Phoenix A, became the key to explaining why this cluster was so extraordinarily luminous in X-rays. The realization that the Phoenix cluster's center housed an active galactic nucleus transformed the search into a full investigation. Astronomers knew that such AGNs are powered by supermassive black holes, objects with masses millions to billions of times that of the Sun, whose gravitational pull is so strong that space itself is bent around them. These black holes are not visible directly, but they can light up the surrounding gas and dust as matter falls toward them. The radiation emitted during this process, especially at X-ray energies, carries the unmistakable signature of material heating under intense gravitational stress, often at tens of millions of degrees. In the Phoenix cluster, this phenomenon was so strong that it outshone the already bright emission from the hot cluster gas, illuminating the central region in X-ray light with record-breaking intensity. But the discovery of the Phoenix cluster and its powerful AGN was not just about finding something bright in X-rays. It was about recognizing an environment where the usual rules seemed to be bending under the weight of extraordinary physical processes. In most massive galaxy clusters, the central supermassive black hole, the engine behind the AGN, pumps energy back into the surrounding gas. This feedback, in the form of jets and outflows, acts like a thermostat, slowing down the cooling of hot gas and suppressing rapid star formation. But in the Phoenix cluster, the evidence suggested something unusual. The cooling gas was not being held back as effectively as in most clusters, leading to massive, runaway cooling and unprecedented production of new stars near the center. This cooling flow was far stronger than anything previously documented, a clue that the energy dynamics in the cluster were being driven by something on a colossal scale. In other words, the Phoenix cluster was not just another beautiful but quiet cosmic structure. It was a cosmic engine room where forces of unimaginable scale were at work, and the central AGN, the black hole powering Phoenix A, was right at its heart. And it was the extraordinarily bright X-ray emissions from this region that told astronomers they had found something fundamentally significant. The X-rays were not just a signal, they were a spotlight, illuminating one of the most energetic and extreme environments ever observed. So how did we go from that first hint in Antarctica's cold skies to where we are today, with telescopes across the globe and in space piecing together the portrait of a cosmic giant? The answer lies in combining technologies that see the universe in different forms of light, converting what would otherwise be invisible processes into a mosaic of data that tells a story. We start with the South Pole Telescope survey, which mapped distortions in the ancient microwave light from the early universe, pointing us toward a region where gravity has sculpted matter on the grandest scale. We follow this with X-ray eyewitness accounts from orbiting observatories like Chandra, capturing the high-energy glow of matter heated to extreme temperatures. We add optical views from Hubble that detail where stars and galaxies sit, and radio imaging that reveals hidden structures inside hot gas and energetic jets. Each piece of this observational puzzle brings us closer to understanding not just the Phoenix cluster itself, but the violent, colliding, cooling and heating processes that govern some of the most massive objects in existence. And at the core of all this lies a simple but profound scientific truth. We detect what we cannot see by observing what it affects. Black holes themselves are invisible, but the matter falling into them becomes some of the brightest light in the universe. Galaxy clusters, like the Phoenix cluster, are invisible from a distance, but the hot gas between galaxies glows so intensely in X-rays that it becomes one of the brightest beacons in the sky. This is how astronomers, with patience, precision and instruments that span wavelengths from radio to X-ray, unraveled the existence and behavior of giant structures billions of light years away, recognizing the black hole. When astronomers first turned their attention toward what we now call the Phoenix cluster, they were not looking for a black hole per se. They were surveying the sky for unusual signatures, patterns and light that did not fit with the ordinary glow of stars and galaxies. Deep space is usually cold and quiet when seen in visible light. But when you look at the universe with X-ray eyes, everything changes. Suddenly, invisible furnaces of energy burst into color and shape, revealing violent processes and energetic engines that cannot be seen by any ordinary telescope. It was through this extraordinary vision, the vision of X-ray observatories, that scientists first realized something remarkable was happening in the heart of the Phoenix cluster. In the early 2000s, data beamed back from space telescopes painted a dramatic picture. Somewhere over 5 billion light-years from Earth, there was an enormous cluster of galaxies that was producing X-rays at levels that broke all known records. The central galaxy in this cluster was glowing more fiercely in X-rays than almost anything astronomers had ever seen. This was not background cosmic noise or the result of millions of stars combined. This was something different, something energetic and extreme. When scientists saw the first X-ray maps of this region, they knew they had stumbled upon an extraordinary cosmic phenomenon. Most galaxy clusters, even massive ones, produce X-rays because the space between galaxies is filled with superheated gas at tens of millions of degrees. This hot plasma glows in highly energetic light that only X-ray telescopes can capture. But what made the Phoenix cluster stand out was the intensity of that glow, especially near the center. The brightness suggested that something was not just hot, but dynamically vibrant, influencing how that gas behaved and radiated energy. The X-ray emission was brightest at the cluster's core, shining like a spotlight at the center of a gigantic cosmic arena. That spotlight was where the extraordinary action was happening. This extraordinary brightness was the first clue that scientists were seeing something atypical. It was a hint that the central galaxy, later named Phoenix A in scientific literature, was hosting something exceptional. But seeing a bright spot in X-rays was just the beginning. It was like hearing thunder. It told astronomers that something powerful was happening, but they still needed to trace the source of the storm. That's where follow-up observations became critical. So scientists pointed telescopes that see different kinds of light toward the Phoenix cluster. They combined data from NASA's Chandra X-ray Observatory, which gives ultra-sharp views of high-energy phenomena, the Hubble Space Telescope, which sees optical light with incredible clarity, and powerful ground arrays like the Karl Jansky Very Large Array VLA, and radio observatories that can detect jets and energetic particle streams invisible in optical light. Each of these observatories added a new layer of understanding to the mystery. What this multi-wavelength detective work revealed was astonishing. In optical and ultraviolet light, telescopes saw not just a giant galaxy, but enormous streams and filaments of cooler gas weaving through it. These ribbons of gas were the raw material for star formation, and unusually, that gas was cooling quickly instead of being heated by surrounding activity, which most massive clusters prevent. The Hubble observation showed that the central galaxy was undergoing an intense burst of star formation, far greater than what we see in typical cluster galaxies. Meanwhile, radio telescopes mapped out structures extending outward from the central galaxy, twin jets of particles moving nearly at the speed of light, a signature sign of what astronomers call an active galactic nucleus, or AGN. These jets are created when a supermassive black hole at the center of a galaxy gobbles up matter. As the matter spirals inward, magnetic forces and intense gravity twist and accelerate particles outward, launching them into space in opposite directions at incredible speeds. The presence of these jets was another piece of evidence pointing toward a powerful feeding black hole at the core. To put it plainly, all the pieces started fitting together like cosmic puzzle parts. The extreme X-ray brightness at the centre, the star-forming filaments of gas, the radio jets, and the optical glow of new stars all pointed to one engine of activity, a supermassive black hole that was actively feeding on matter around it. This feeding process, matter falling toward the black hole, heating up and emitting intense radiation, is exactly what astronomers expect from the central engines of active galaxies. In simple terms, Phoenix A's nucleus was lit up because something gigantic and hungry was at work. It is this combination of signatures, intense X-ray glow, gas cooling rapidly, energetic jets shooting out from opposite sides, and enhanced star formation that separates the central region of the Phoenix cluster from most other galaxy clusters known to science. In most massive clusters, the black holes at their centers are powerful enough to heat the surrounding gas and suppress star formation, acting like a thermostat that prevents gas from cooling. But in the Phoenix cluster, the black hole's influence seemed to allow, or even encourage, rapid cooling in places, a twist on the usual narrative. This unexpected behavior revealed something new about how black holes and their environments interact. Let's focus on the X-rays for a moment, because this was the first, and perhaps most dramatic, sign that something huge was happening. X-rays are produced when matter reaches extraordinary temperatures, often millions of degrees. In the Phoenix cluster, the X-ray glow was far stronger than what scientists had seen from comparable clusters. When NASA's Chandra looked at this region, it saw bright purple hues of hot gas in the images it produced, gas that had been heated up by gravitational forces and dynamic motion on a massive scale. That X-ray emission wasn't static or faint. It was dynamic and powerful, indicating that the environment was being stirred by something energetic and extreme. The level of X-rays in the center was so intense that it suggested the presence of a giant that was not just heating its surroundings, but playing a dominant role in shaping them. Astronomers realized that the only mechanism that could produce such intense X-ray radiation from a single, compact region at the center of a galaxy cluster was a supermassive black hole feeding on gas and dust at an extraordinary rate. This type of feeding process, called an accretion flow, causes material to get squeezed and heated to incredible temperatures, which in turn produces powerful X-rays. The pattern and intensity of the radiation fit exactly what scientists expect from an active black hole engine. But this was not one of those quiet black holes that sit dormant in the centers of galaxies, barely affecting their surroundings. This black hole was active, bright, energetic, and influencing everything near it. The radio jets seen by ground telescopes were another clear sign of this activity. These jets are not only powerful, but also directional. They stretch outward from either side of the nucleus, like immense cosmic arms. In other systems, similar jets are known to blow cavities or bubbles in the surrounding hot gas, structures that show up as faint but clear features in X-ray images. Scientists studying the Phoenix cluster found evidence of such cavities, suggesting that the black hole's activity was carving structures into the hot gas around it, sculpting the cluster core itself. At this point, the picture had become unmistakable. The extreme X-ray brightness was not an anomaly or a random fluctuation. It was the footprint of a supermassive black hole, one that was actively feeding and shaping its surroundings, tugging at gas and dust with such power that it left an unmistakable mark across the electromagnetic spectrum. From X-ray to radio, the signatures aligned with what astronomers understand about black holes in their feeding phases, where matter falls inward and energy radiates outward in patterns that can be detected across billions of light years. Despite the clarity of these observations, this was not a simple story. It wasn't just that the black hole was active, it was that it seemed to behave differently from other black holes observed in galaxy clusters. In most massive clusters, the central black hole's activity suppresses star formation by keeping the surrounding gas too hot to condense. But around Phoenix A, astronomers observed cooling gas filaments and an unusually high rate of star birth. This dual nature, an active black hole and rapid cooling, set the Phoenix cluster apart from almost every other known system, suggesting a more nuanced interplay between feeding black holes and their environments than scientists had previously thought. Modelling gravitational effects and radiation output. When scientists finally began to estimate its mass, Phoenix A didn't just shine on X-ray maps. It redefined what we thought was possible for black holes in the universe. The ways astronomers measure the weight of something so distant and invisible are not the same as putting it on a scale, of course. In the case of Phoenix A, the black hole at the heart of the Phoenix cluster, scientists relied on how it affects the matter around it and how much energy it radiates as it feasts on gas and dust. By building complex models of gravity and energy, and by watching how the hot gas in the cluster behaves under the pull of an unseen powerhouse, researchers pieced together a picture of a black hole that is truly immense compared to almost everything else we know in the cosmos. Imagine standing on a distant world and looking past swirling galaxies into the deep darkness between stars. There, buried at the center of a massive galaxy cluster, lies a black hole so enormous that its gravitational influence shapes the motion of millions of stars and clouds of gas. The mass of this black hole is not measured in millions of suns, the way smaller black holes often are, but in tens of billions of suns. In the case of Phoenix A, modelling suggests its mass could be on the order of 100 billion times the mass of our Sun, and potentially more. This is not a rough guess, it is a scientific estimate based on how the black hole's gravity influences the density of stars and the behaviour of hot gas in its host galaxy, and how the energy output from the black hole interacts with the intracluster medium. To understand what that figure means, it helps to compare Phoenix A's mass with other famous black holes. The supermassive black hole at the centre of our own galaxy, known as Sagittarius A star, weighs in at about 4 million solar masses, which sounds large until you put it next to Phoenix A's estimated mass. Phoenix A is tens of thousands of times more massive than our home galaxy's central black hole, a fact that sounds almost surreal when you say it out loud. This enormous mass places Phoenix A in a category of black holes that scientists sometimes refer to as stupendously large black holes, objects that challenge our understanding of how supermassive black holes form and grow over cosmic history. Estimating the mass of a black hole so distant and enormous is not simple. Astronomers cannot directly see the black hole, and they cannot track stars orbiting around it in the same way they can for closer black holes. Instead, scientists observe how the black hole affects the hot gas and energy in its environment. In the center of the Phoenix cluster, there is more hot gas than in almost any other known cluster, glowing fiercely in X-ray light and feeding the black hole as it grows. By building models that take into account how gravity, pressure and energy interact, researchers can infer how much mass must be present to produce the observed effects. In essence, the black hole's immense presence is revealed not by direct imaging, but by the way it shapes the motions and energies of everything around it. Those models go even further. They take into account the rate at which the hot gas in the cluster cools and falls toward the center, how much energy the black hole's active galactic nucleus, AGN, must release to counteract that cooling, and how the density of stars and gas changes toward the heart of the central galaxy. Combining all of these data points with theoretical calculations, scientists build computer simulations that describe how a black hole like Phoenix A would influence its environment. When the simulations match the real cosmic observations, that gives astronomers confidence that their mass estimate is reasonable, even if the black hole itself remains invisible. What makes Phoenix A stand out among even the largest black holes known is just how extreme its mass estimate is. Other candidates like TON 618, another titanic black hole discovered in a distant quasar, were estimated to have masses on the order of tens of billions of times the Sun. TINE 618's black hole, for example, is often quoted around 66 billion solar masses, a staggering number by any standard. But Phoenix A's estimated mass being so close to 100 billion solar masses or more suggests that it might be the most massive black hole humanity has ever detected in the observable universe. This enormous mass is based on how intensely the black hole must be affecting its galaxy and cluster core, and how much energy it must be producing as it feeds on the surrounding gas. This extreme mass has dramatic consequences. A black hole with the weight of tens of billions, or even 100 billion suns, would have an event horizon, the invisible boundary beyond which nothing can escape, so large that if it were placed at the centre of our own solar system, it could stretch far beyond the orbit of Pluto. The region around such a black hole would warp space-time on enormous scales, bending light from nearby stars and altering the paths of matter falling toward it. This enormous gravitational influence is not just theoretical, it is reflected in the energetic dynamics of the Phoenix Cluster's central galaxy, where vast streams of hot gas, powerful jets, and intense star formation are all connected to the presence of this black hole's dominance. The ways scientists estimate such immense masses rely on deep understanding of physics. Gravity tells us how matter should move, and the radiation we observe tells us how much energy is being released as matter accelerates and heats up before crossing that invisible event horizon. In the case of Phoenix A, the X-ray brightness of the central region, the cooling flow of gas into the cluster core, and the structure of the galaxy itself all point to a central source with enormous gravitational pull. By comparing these observations with known physical laws, such as the relationship between gravitational influence and orbital motion, the physics of heated gas, and the dynamics of active galactic nuclei, astronomers can build a consistent picture that explains the observed data. That picture shows a black hole of mind-bending mass at the heart of Phoenix A. This process of modelling is not purely speculative. It draws on decades of research into how galaxies evolve, how matter behaves under extreme gravitational forces, and how black holes grow by accreting surrounding material. When scientists model a black hole's influence on its surroundings, they are not guessing randomly. They are applying precise equations that have been tested in many other contexts, from the orbits of stars around Sagittarius, a star in our own galaxy, to the motion of gas in quasars billions of light years away. These equations tie together gravity, energy, and motion in ways that allow astronomers to infer the presence and mass of objects that can never be seen directly. The result of these models and observations is a staggering figure that pushes the limits of our cosmic scale. Phoenix A's black hole is estimated to weigh around 100 billion suns, or possibly more. In comparison, most galaxies in the universe have central black holes that are millions to a few billion solar masses. Phoenix A dwarfs them all, rising into a realm of black hole mass that is almost unimaginable. To put it in another perspective, if we could somehow compress all the stars in the Milky Way into a single point, the black hole in Phoenix A would still outweigh that entire collection by many times. This scale of mass reshapes how astronomers think about the extremes of black hole formation and growth in the universe. But this massive estimate comes with its own scientific puzzles. If Phoenix A's black hole truly is near 100 billion solar masses, it challenges conventional theories about how black holes grow. Black holes gain mass by accretion, pulling in gas, dust, and even stars, and by merging with other black holes over cosmic time. But the physics of accretion has natural limits, because as matter falls in and emits energy, that energy can push back on the surrounding gas, slowing further growth. For a black hole to reach the mass of tens of billions or 100 billion suns, it would have to remain in an environment rich with gas and experience conditions that allow sustained feeding over billions of years. The Phoenix Cluster's central region, with its enormous supplies of hot gas and cooling flows that feed the core, may provide precisely those conditions, allowing Phoenix A to grow larger than nearly any other known black hole. What makes the modelling even more compelling is that it incorporates not just the central galaxy's own structure, but the interaction of that galaxy with the cluster's hot intracluster medium. In galaxy clusters, vast reservoirs of superheated gas, often millions of degrees in temperature, fill the space between individual galaxies. In most clusters, the central black hole's activity prevents this gas from cooling rapidly because the energy released by the AGN heats the gas and suppresses star formation. But in the Phoenix cluster, the cooling gas seems to flow into the cluster core more rapidly, feeding both the black hole and intense star formation in the central galaxy. This unusual combination of cooling and energetic activity provides a unique laboratory for studying how a black hole can grow to such incredible mass. The figures that emerge from these models, tens of billions to around 100 billion solar masses, place Phoenix A's black hole among the most massive ever estimated in the observable universe. It blurs the line between what was once thought to be the upper limits of black hole mass and what the universe can actually produce. As scientists refine their models and gather more data, the picture may sharpen further, but the current estimates already make Phoenix A one of the most extraordinary cosmic objects ever studied. What makes Phoenix A so huge? To understand how huge Phoenix A truly is, we must first strip away the familiar images and expectations we have about black holes. In movies or popular culture, black holes are often shown as swirling vortexes, sucking in everything nearby. But in real astronomy, black holes are not defined by what they look like. They are defined by their mass, how much stuff they contain, and how that mass shapes the space and motion around them. The way scientists measure and compare black holes does not rely on visuals, but on understanding their mass scale. When we talk about mass in the universe, we measure it not in kilograms or pounds, but in terms of solar masses, how many times more massive an object is compared to our Sun. That single measure allows astronomers to place black holes into different categories, from the smallest kinds born from dying stars to the most gargantuan engines in the hearts of distant galaxies. Phoenix A, the central black hole of one of the brightest and most energetic galaxy clusters ever observed, sits at an extreme end of this cosmic scale. And to grasp its place, we need to walk through the spectrum of black hole masses, one category at a time. At the smallest end of the black hole, family are stellar mass black holes. These are the ones formed when a massive star, tens of times heavier than our Sun, reaches the end of its life and collapses under its own gravity. In that moment, the core of the star compacts until it becomes an object whose gravity is so intense that nothing can escape once it crosses its event horizon. Stellar mass black holes typically range from about 5 to perhaps a few dozen times the mass of the Sun. They are huge compared to anything we experience on Earth, but in the cosmic scheme of mass, they are the small ones. Scientists have detected many of these by watching how they tug on companion stars in binary systems or through the X-rays produced when material spirals into them from nearby gas. Even these stellar black holes, extraordinary as they are only the first rung on the ladder of black hole sizes. Above stellar mass black holes is a class called supermassive black holes. These are not the remnants of dying stars, but ancient central engines of galaxies themselves. When astronomers observe the centers of spiral, elliptical, and other kinds of galaxies, nearly all of them show evidence of harboring a black hole with millions to billions of solar masses. Our own galaxy, the Milky Way, has one of these supermassive black holes at its heart, called Sagittarius, a star. It weighs about 4 million times the mass of the Sun, a figure that sounds huge when you say it, because it is huge, far beyond human experience. But when compared with even larger black holes in other galaxies, Sagittarius A star is on the modest side of the supermassive club. Supermassive black holes are thought to grow over time by accreting gas, dust, and stars, and sometimes by merging with other black holes in violent cosmic collisions. They sit at the centers of galaxies and, through their immense gravity and energetic activity, influence star formation, gas motion, and the structure of their host systems. The growth of these black holes plays a key role in how galaxies evolve, and for decades scientists have considered them among the most massive objects in the known universe. Yet as astronomers peered deeper into the cosmos and studied more powerful cosmic engines, they realized that some black holes are significantly more massive than the typical supermassive ones. These extraordinary objects fall into a subclass that scientists refer to as ultramassive black holes. While the lower end of supermassive black holes caps out in the billions of solar masses, ultramassive black holes exist in a realm where masses exceed roughly 10 billion solar masses. Some may tip the scale at 20, 50, or even 60 billion solar masses. These black holes are often found at the centers of the most massive galaxies in rich clusters, or in the luminous cores of quasars, objects so bright that they outshine entire galaxies even across cosmic distances. What sets ultramassive black holes apart is not a different physical law, but simply scale. They are the same type of object as other supermassive black holes, only orders of magnitude heavier. Their gravitational pull, event horizon size, and energy output grow directly with the amount of mass they contain, and because they sit in dense cosmic environments with abundant gas and frequent interactions, they have had more opportunities over cosmic time to accrete matter and merge with other black holes. Even beyond ultramassive black holes, scientists have proposed the possibility of an even more extreme category, sometimes called stupendously large black holes, or slabs for short. This term is used to describe hypothetical black holes whose masses could reach into the hundreds of billions or even trillions of times the mass of the Sun. The idea of slabs stems from theoretical models and the observation that some black holes appear to push the upper limits of what we understand about black hole growth. These objects would be truly gigantic, stretching their influence over distances far larger than even entire solar systems, and potentially dominating the dynamics of their host clusters and cosmic neighborhoods in ways that dwarf ordinary galaxies. While slabs remain largely theoretical and observationally controversial, the mere possibility of their existence highlights just how broad the range of black hole masses can be in the universe and how much we still have to learn about the extremes of cosmic gravity. Now, placed within this spectrum, from stellar mass to supermassive to ultramassive, and into the hypothetical realm of slabs, Phoenix A's black hole clearly sits among the heaviest black holes ever discovered. Based on the gravitational effects it has on the hot gas and stars in the Phoenix cluster, and the staggering amount of energy radiated from its active galactic nucleus, scientists estimate its mass to be on the order of tens of billions of solar masses, and potentially up to around 100 billion solar masses or more. That places Phoenix A squarely in the ultramassive category, an elite group of cosmic engines whose sheer mass stretches the boundaries of what we once believed was a limit. To say that this black hole is heavy is an understatement. It is so massive that if we imagine replacing our Sun with Phoenix A's black hole, its gravitational influence would reach far beyond the orbit of Pluto, encompassing distances measured in hundreds of astronomical units. That scale, a gravitational footprint larger than the entire region inhabited by the planets of our own solar system, helps us begin to grasp how enormous this object really is. When astronomers first realized that Phoenix A's mass might be in this extreme range, it marked a profound shift in how scientists think about the most massive black holes in the universe. Not long ago, black holes weighing tens of billions of solar masses were considered rare exceptions, outliers among supermassive black holes. Phoenix A, with its estimated mass near the hundreds of billions range, pushes even that boundary, nudging astronomers to reconsider how such massive objects can form and grow over cosmic history. The Phoenix cluster's central galaxy, with its deeply energetic core, provided the conditions necessary for such a black hole to feed and expand over time, drawing in vast amounts of gas and dust from its surroundings. As that material spiraled inward, it heated up and radiated energy across the electromagnetic spectrum, powering the cluster core's incredible X-ray brightness and fueling energetic jets detected in radio wavelengths. Every line of evidence pointed to a central black hole of astonishing mass, far beyond the typical supermassive black holes found in more tranquil galactic centers. Understanding that Phoenix A belongs in the ultramassive category also helps scientists place it in context with other massive black holes observed across the universe. For example, the quasar TON 618, one of the most famous and massive black holes known, has an estimated mass in the tens of billions of solar masses, often cited around 60-odd billion. That figure was once considered near the upper limit of black hole mass estimates. Phoenix A's mass estimate, being so much higher, challenges that assumption and suggests that the universe can produce black holes of even greater magnitude, given the right conditions. These conditions include being embedded in a rich, gas-filled environment where cooling flows of hot gas can funnel matter toward the center without being entirely quenched by the energy output of the active galactic nucleus itself. In the Phoenix cluster, that cooling flow appears unusually strong, feeding both the central black hole and an intense period of star formation in the host galaxy. A rare and striking combination that makes the system a natural laboratory for studying black hole growth on the grandest scales. The way scientists determine that Phoenix A's black hole is ultramassive involves detailed modeling of the gravitational effects it has on the environment around it. Because we cannot look directly at the black hole, its event horizon is invisible by definition. Researchers analyze how the hot gas in the cluster core behaves, how much energy it radiates, and how the mass distribution of stars and gas changes toward the center of the galaxy. By feeding all these observational data into computer models that account for gravity, pressure, and the physics of hot plasma, astronomers can estimate how much mass must be present to explain what they observe. When those models converge on a mass near tens of billions, or around 100 billion solar masses, it places Phoenix A among the most massive black holes ever recorded. This process of indirect measurement is not uncertain speculation. It relies on well-tested physical laws that describe how matter behaves under gravity and how energy is emitted when material is heated to extreme temperatures near a black hole's accretion disk. The result is a consistent picture of a black hole whose mass dwarfs that of most others we know, and whose influence shapes everything from the motion of hot gas to the rate of star formation in its host galaxy. The fact that Phoenix A is ultramassive tells us something important not just about this particular black hole, but about the universe itself. It implies that under certain conditions, clusters filled with hot gas, galaxies interacting and merging over billions of years, cooling flows that funnel matter inward, black holes can continue to grow long after the early epochs of cosmic history. In simpler environments, supermassive black holes may reach a plateau, their feeding slowed by feedback processes that heat surrounding gas and prevent further accretion. In the Phoenix cluster, however, the balance appears different, allowing sustained growth and creating one of the heaviest black holes already observed. This insight adds a new dimension to how astrophysicists think about black hole evolution, connecting the dots between cosmic environments, cooling flows, star formation, and the ultimate mass that a black hole can achieve. When we place Phoenix A within the black hole mass scale, from stellar mass to supermassive to ultramassive, it becomes clear that this object represents something extraordinary. It sits on the upper end of the ultramassive category, perhaps brushing against the lower theoretical edges of slab territory, yet still grounded in the physics we observe across the cosmos. Its mass estimate sits not as a vague possibility, but as the best fit to the data we have, tens of billions of solar masses, possibly approaching 100 billion. In the vast landscape of cosmic structures, Phoenix A is not just a heavy object, it is a record-shaking contender, a benchmark that expands our sense of what black holes can become when matter and gravity conspire over billions of years. In terms of sheer gravitational influence, an ultramassive black hole like Phoenix A bends space and time on scales far beyond what we see in smaller systems. Its gravitational pull reaches outward, shaping the motion of hot gas and stars, dictating how energy flows in the cluster core, and creating a dynamic environment where physics operates at its most extreme. Compare Phoenix A to Sagittarius A star. When we talk about something as huge as a black hole that weighs around 100 billion times as much as the Sun, the first reaction most people have is, that number is too big to understand. And that reaction is completely normal. We never deal with numbers like that in everyday life, but we can make these numbers make sense by comparing Phoenix A to things people already know. Our own black hole at the center of this galaxy, the size of our solar system, and even other record-breaking black holes that astronomers have found in the cosmos. In the center of our own Milky Way galaxy lies a black hole called Sagittarius A star. Scientists have measured its mass very carefully by watching stars orbit around it. Stars near the center of the Milky Way move faster and in tighter loops because they are responding to the invisible pull of something incredibly heavy. After decades of tracking these motions, scientists concluded that Sagittarius A star weighs about 4 million times the mass of the Sun. This is enormous compared to anything we experience on Earth, but when compared with the mass of Phoenix A's black hole, it becomes a helpful way to build scale. If Phoenix A's black hole weighs roughly 100 billion solar masses, then it is about 24,000 times more massive than Sagittarius A star. Think about that for a moment. If you took Sagittarius A star and then multiplied its mass by 10,000 and then again by more than 10,000, you still wouldn't reach Phoenix A's mass. This isn't a small increase or a big jump. This is a scale that pushes well beyond ordinary comprehension. When we say Phoenix A is more massive than Sagittarius A star by a factor of tens of thousands, we are talking about enormous gravitational influence that affects entire galaxies, and even the space around them in ways that are nothing like what we see in our own galactic center. Let's put that into picture form. If you imagine the Milky Way as a small city on a map, then Phoenix A's black hole would be something like an entire continent in weight. Sagittarius A star might be one building in that city, but Phoenix A's black hole would be a landmass so big that it reshapes the world around it. This kind of comparison isn't meant to be poetic. It's meant to help viewers visualize how orders of magnitude work in space. Now let's go a bit deeper into what this means in terms of physical size, not just mass. Black holes don't have surfaces like planets do. What they have instead is something called the event horizon. That is the invisible boundary around a black hole. Inside the event horizon, gravity is so strong that nothing can escape, not even light. The radius of this boundary, how far it extends from the center, depends directly on the black hole's mass. The more mass, the larger that boundary is. For Sagittarius A star, the event horizon is about 12 million kilometers in radius. That might sound big, but let's compare that to everyday distances in space. The distance from Earth to the Sun is about 150 million kilometers, so the radius of Sagittarius A star's event horizon is only a small fraction of that, smaller than the distance from Mercury to the Sun. That's huge in human terms, but small in cosmic terms. Phoenix A's event horizon, on the other hand, is a very different scale. If it truly weighs near 100 billion suns, its event horizon would stretch outward by hundreds of astronomical units. An astronomical unit, or AU, is the average distance between Earth and the Sun. That means Phoenix A's event horizon would be so wide that it could include the space of our entire solar system and more, reaching beyond the orbit of Pluto. Pluto orbits the Sun at almost 40 astronomical units from the centre of our solar system. If Phoenix A's event horizon sits at something like 200 to 300 astronomical units, then it is 5 to 7 times larger than the orbit of Pluto. That is hard to picture because nothing in our normal experience spans distances like that. But in cosmic terms, this tells us that Phoenix A's gravity reaches out far enough to dominate an entire region of space that, in our own corner of the universe, would include the Sun, all the planets, the asteroid belt, and distant dwarf planets. This doesn't mean Phoenix A's black hole swallowed all those objects. It means its gravitational boundary is that wide. Keep in mind that when we talk about an event horizon spanning hundreds of astronomical units, we are not talking about the visible object, because black holes don't have a visible surface. Instead, we are talking about the radius of influence, the invisible boundary where gravity becomes absolute and unstoppable. Inside that boundary, space-time is bent so intensely that even light cannot escape. But what lies outside that boundary? Stars, gas, dust, even radiation can still be affected by the black hole's pull, and that influence can extend for thousands of astronomical units beyond the event horizon itself. Now that we've compared Phoenix A to Sagittarius A star and visualized how large its event horizon might be, let's compare Phoenix A to some of the other largest black holes ever discovered. One of the most famous record holders before Phoenix A entered the picture was a black hole found at the center of a distant quasar called TON 618. Quasars are extremely bright cores of galaxies powered by massive black holes feeding on matter. TON 618's black hole is one of the most massive black holes ever measured through direct observation of its light and the motion of nearby matter. Scientists estimate TON 618's black hole to be around 60 to 70 billion times the mass of the Sun. Pause and take that in. 60 to 70 billion solar masses is already huge when compared to the Sun, and it was once considered one of the biggest black holes ever found. But Phoenix A's black hole, with a mass near 100 billion solar masses or more, would surpass TON 618 by a wide margin. In simple terms, Phoenix A is heavier than TON 618 by tens of billions of solar masses. Let's use a straightforward analogy to help this comparison sink in. Imagine a group of giant cargo ships on the ocean. Sagittarius A star would be like a large tanker ship, big, heavy, moving tons of weight, but still part of the regular traffic of cosmic things. TON 618's black hole would be like an enormous aircraft carrier, a supermassive vessel spanning a huge distance. But Phoenix A's black hole, it would be like a whole fleet of aircraft carriers tied together, stretching wider than anything the ocean has ever seen. This is not to say Phoenix A is literally a cluster of black holes, but that its mass dwarfs what once seemed like the biggest possible black hole. These comparisons are not just impressive numbers on paper. They matter because they show us how the universe builds structures. Most black holes we observe, even the supermassive ones, tend to sit quietly at the centers of galaxies, shaping their environment, but not dominating more than a tiny range around them. Phoenix A breaks that pattern. Its mass and size tell scientists that something in its environment, one of the largest galaxy clusters ever observed, has fed it vast amounts of matter over billions of years. Enough matter to make it not just big, but almost unbelievably huge compared to the familiar black holes we often hear about. Phoenix A's mass also tells us something about how gravity works on huge scales. The stronger the gravity, the more it pulls in matter from all directions. A black hole with 100 billion solar masses doesn't just sit quietly. It shapes the motion of stars, pulls on gas across enormous regions, and affects the way galaxies around it behave. The gravitational pull at that scale influences not just the heart of a galaxy, but entire clusters of galaxies. This is one of the reasons astronomers are so fascinated by Phoenix A. It is not just a big object, it is a cosmic heavyweight that influences its entire neighborhood. Another way to understand Phoenix A's size is to think about light itself. Light near a black hole escapes only if it is outside the event horizon. Inside that boundary, light falls in, never to return. For a black hole as massive as Phoenix A, the event horizon would trap light over distances greater than anything in our solar system. If you stood near that boundary, were it possible to stand near a black hole, light travelling from further away would never reach you if it tried to climb out. This shows that the scale of Phoenix A's gravity is not just a number, it is a boundary in space that defines what can or cannot escape its pull. When we compare Phoenix A to smaller black holes like Sagittarius A star and to record holders like TON 618, one thing becomes clear. Phoenix A is not just bigger, it is in a class of its own. It stretches the limits of what we thought black holes could become. In the cosmic hierarchy of weight and influence, Phoenix A stands near the top, heavier and more powerful than nearly every other black hole ever measured. Now let's go back to our own solar system to see one more comparison. The distance from the Sun to Neptune, the farthest of the 8 major planets, is about 30 astronomical units. The distance to Pluto, a dwarf planet, is about 40 astronomical units. If Phoenix A's event horizon extends outward hundreds of astronomical units, then it could easily cover all the space from the Sun to well beyond Pluto. That means its gravitational boundary would include the entire region that in our own system contains planets, moons, asteroids, and comets. When we picture that scale, something so massive and wide that it could span the equivalent of our whole solar system, then we begin to grasp what astronomers mean when they say, this is one of the largest black holes ever detected. Some people find it helpful to compare such distances with everyday things. If an astronomical unit were like one step, then Phoenix A's event horizon would cover hundreds of steps. But those are not normal steps. Those are steps measured in millions of kilometres. A single astronomical unit is nearly 150 million kilometres. Hundreds of AU would be tens of billions of kilometres. That's not a stretch or an exaggeration. That is real, measurable space. It is bigger than any distance humans have ever travelled with spacecraft. Scientists use all of these comparisons to help viewers and students visualise something that is otherwise too large to picture. Phoenix R is not just heavy, it is in a realm where our usual sense of big no longer applies. Words like massive and huge only begin to hint at the scale. It is hundreds of times wider than black holes like Sagittarius A star, and tens of billions of solar masses heavier than objects like TON 618. And yet, when scientists talk about structures that shape the universe, galaxy clusters, superclusters, cosmic filaments, they always come back to gravity. Gravity is what holds these objects together. It is what pulled the material in the early universe to form stars, galaxies, and eventually clusters, like the one that hosts Phoenix A. Phoenix A's black hole is a dramatic demonstration of how gravity, acting over billions of years, can gather matter into something that bends space and time itself on enormous scales. Most black holes we know about are quiet, not feeding actively, not growing quickly, and not producing huge amounts of radiation. But Phoenix A's black hole is different. It sits in a rich environment full of gas and dust that can be pulled in and heated to extreme temperatures. As material falls in, it releases energy that scientists detect as bright X-rays and other forms of light. This is one of the reasons Phoenix A's event horizon is not just big because of its mass. It is big because it is actively growing. Every piece of matter that falls in adds to its mass, and every bit of mass it gains adds to the size of its event horizon. It is a self-strengthening engine of gravity. When we compare that dynamic growing engine to other black holes, what stands out is not just weight, but influence. Phoenix A does not just sit quietly, it shapes its surroundings. It pulls on gas, controls star formation in its host galaxy, and affects the motion of billions of particles and fields around it. Its reach, defined by its event horizon size and mass, stretches far beyond what we once thought possible for black holes. None of this is science fiction. These are measurements taken by real telescopes, processed through real physics, and confirmed by multiple lines of evidence from X-ray light, radio observations, and models of gravity and matter motion. When scientists say Phoenix A may be the most massive black hole ever detected, they are not guessing. They are reporting what the data shows: a black hole heavier than Sagittarius A by about 24,000 times, heavier than TON 618 by tens of billions of solar masses, and with an event horizon that could stretch well beyond the outer edges of a solar system equivalent to our own. These comparisons help turn a number that seems abstract, 100 billion, into a picture that people can begin to understand. Because Phoenix A is not just a big number on a chart, it is a cosmic giant, a gravitational powerhouse whose size and mass fundamentally reshape the region around it. When astronomers look at this black hole, they see not just the largest known gravitational object in a galaxy cluster, but a new way of understanding how massive the universe can make something when given enough time and material. Accretion and feeding. To understand how Phoenix A became such a colossal black hole, we need to look at the physics that allows black holes to grow. Unlike stars, which shine because of nuclear fusion, black holes grow by pulling in matter from their surroundings. This process, known as accretion, is the primary way they gain mass over time. Every black hole, from the smallest stellar mass types to ultramassive giants like Phoenix A, relies on accretion to reach the staggering sizes we observe today. Accretion is not a simple process. Matter doesn't just fall straight into a black hole. Instead, gas, dust, and even stars orbit the black hole in a disk-shaped flow called an accretion disk. The material in this disk spirals inward slowly, drawn by the black hole's immense gravity. As it moves closer, the material rubs against itself and heats up, sometimes to millions of degrees, producing intense radiation, especially in X-ray wavelengths. This radiation is one of the main ways astronomers detect and study black holes, particularly ones that are far away. Without this energetic glow, a black hole would be completely invisible, and we would only notice its gravity indirectly by watching how it affects nearby objects. Phoenix A's growth was made possible because it sits in an extraordinary environment, the Phoenix cluster. This cluster is one of the brightest X-ray clusters ever observed, and it is rich in hot, dense gas. The gas is the fuel that allows the black hole to feed continuously. Unlike isolated black holes that might have limited nearby material, Phoenix A has a near constant supply of gas streaming toward it. This gas flows from the surrounding cluster, slowly cooling as it moves inward. In many clusters, the energy output of the central black hole pushes gas away, creating a feedback loop that limits growth. But in the Phoenix cluster, the gas is so abundant and dense that the black hole can keep feeding despite its own radiation. Accretion isn't the only way Phoenix A grew. Mergers with other black holes also play a crucial role. Galaxy clusters are crowded environments where galaxies frequently collide and merge. When two galaxies merge, their central black holes eventually come together as well, forming a single, more massive black hole. This process can happen multiple times over billions of years, each collision contributing additional mass. In the dense Phoenix cluster, where galaxy interactions are common, Phoenix A likely experienced multiple mergers, each adding tens of millions or even billions of solar masses to its total. Stars can also feed black holes, although this is a smaller contribution compared to gas and mergers. If a star strays too close to a black hole, the immense tidal forces can rip it apart in a process called a tidal disruption event. The remnants of the star then spiral into the black hole, adding to its mass and producing a temporary flare of light. While each star adds only a fraction of the mass compared to gas inflows or mergers over billions of years, these events can accumulate and contribute significantly, especially in environments with dense stellar populations. The combination of gas inflow, mergers, and stellar disruption creates a perfect storm for black hole growth in a cluster like Phoenix. Unlike black holes in quieter galaxies, Phoenix A had access to enormous amounts of material. The cluster's central galaxy is not only the largest galaxy in its local environment, but also sits at the bottom of a gravitational well filled with hot, dense gas. The gas is slowly cooling and flowing inward, feeding both the black hole and star formation in the galaxy simultaneously. This dual process is rare because most massive black holes in clusters suppress star formation by heating surrounding gas. Phoenix A is unusual because the cooling flow is strong enough to allow both the black hole to grow and new stars to form, creating an ultra-rich active galactic nucleus. The physics behind accretion is also fascinating because of the energy involved. As gas falls into the black hole, it converts gravitational potential energy into heat and light. For a black hole as massive as Phoenix A, the amount of energy released is unimaginable. Every kilogram of gas falling in can produce more energy than our Sun emits over millions of years. This is why the Phoenix cluster shines so brightly in X-rays, and why astronomers initially detected the black hole in the first place. By measuring the energy output and modelling how gas moves in the cluster, scientists can estimate the black hole's mass with astonishing accuracy. Mergers contribute to growth in a slightly different way. When two black holes collide, the event releases gravitational waves, ripples in space-time predicted by Einstein and now detected by instruments like LIGO. In clusters as massive as Phoenix, repeated mergers over billions of years would have built Phoenix A into the ultramassive black hole we observe today. Each merger not only adds mass, but also redistributes angular momentum and can temporarily disturb the surrounding gas, increasing accretion rates and triggering bursts of radiation. Even small events matter. As stars orbit near the black hole, some will gradually lose energy through interactions with gas or other stars, and eventually spiral inward. Over billions of years, these small contributions combine with the inflow of gas and major mergers to create a black hole of truly unprecedented mass. This is why Phoenix A is so different from the black holes we observe in smaller galaxies. It has been feeding continuously in a perfect environment for growth. Phoenix A's feeding frenzy is still ongoing. Observations show active accretion, meaning the black hole is still consuming gas from its surroundings. The X-ray radiation is one of the brightest ever seen from a black hole in a cluster, indicating enormous ongoing energy release. The accretion process is efficient because the black hole sits at the bottom of a dense cluster with abundant fuel. Unlike black holes in isolated galaxies that may starve once nearby gas is used up, Phoenix A's environment guarantees a nearly continuous supply of material. The scale of accretion here is hard to overstate. For a black hole of 100 billion solar masses, even tiny amounts of gas added over millions of years represent enormous amounts of mass. Imagine a single cloud of gas containing a billion suns worth of material falling into the black hole. This is like adding another Ton 618-sized black hole to the mix. Over billions of years, repeated inflows of gas, multiple mergers and stellar disruptions have likely made Phoenix A the largest known black hole in its galaxy cluster, and possibly one of the largest in the universe. The environment of the Phoenix cluster also provides clues about how feedback and growth balance. Typically, active black holes release so much energy that they heat surrounding gas, preventing further accretion. This self-regulation is why many clusters don't produce ultramassive black holes. Phoenix A, however, sits in a gas-rich cluster where the cooling flow is strong enough to counteract this feedback. This creates a unique situation. The black hole grows while the cluster remains luminous and active. All of these feeding mechanisms, gas accretion, mergers and stellar disruptions, work together in a way that pushes Phoenix A into the category of ultramassive black holes. While most black holes reach only a few billion solar masses, Phoenix A has grown far beyond, thanks to its perfect combination of environment, time, and continuous feeding. The black hole's size is not accidental. It is the natural outcome of physics operating over billions of years in an unusually dense, gas-rich and dynamic environment. Even today, Phoenix A is still accumulating mass. Each observation shows new X-ray emissions and evidence of high-energy radiation from the accretion disk. The cluster's central galaxy continues to funnel material inward, feeding the black hole and sometimes producing star formation in the same region. This ongoing feeding process ensures that Phoenix A remains alive, growing and changing, unlike many black holes that have become dormant over cosmic time. Active galactic nuclei. When we talk about Phoenix A, we're not just talking about a massive black hole sitting quietly at the center of its galaxy. No, this black hole is the heart of an active galactic nucleus, or AGN, which is basically a galaxy's engine running on pure gravity. An AGN forms when matter, gas, dust, maybe even stray stars, falls toward a supermassive black hole. As this material spirals inward, it doesn't just disappear. It heats up, spins faster, and shines with enormous energy. This energy comes from the process of accretion, but on a scale that makes anything we see in the Milky Way look tiny. The infalling material releases radiation across the electromagnetic spectrum. That means X-rays, ultraviolet light, visible light, infrared, and even radio waves can all stream out from around the black hole. Observers on Earth can pick up this radiation with telescopes designed for these different wavelengths, and that's often how we first detect AGNs, a galaxy glowing far brighter than it should just from its stars alone. Phoenix A's AGN is powered by the infall of matter into a black hole hundreds of billions of times heavier than the Sun. Imagine the amount of energy released when that much gas, dust and debris accelerates toward the black hole, heats up to millions of degrees and emits radiation across space. The X-ray light from Phoenix A is so bright that it first caught the attention of astronomers using space-based telescopes. It's like a cosmic lighthouse, signaling the presence of an enormous feeding black hole in a galaxy cluster billions of light years away. Some AGNs, especially the most powerful ones, can also produce relativistic jets. These are streams of particles launched outward from near the black hole at speeds close to the speed of light. They don't shoot from the event horizon itself, but from the region just outside it in the hot spinning accretion disk where magnetic fields twist and fling matter outward. If Phoenix A has these jets, and deep observations suggest it might, they would stretch for thousands, maybe even hundreds of thousands of light years, carrying energy far beyond the central galaxy and affecting the entire Phoenix cluster. These jets can heat the surrounding gas, suppress star formation in nearby galaxies, and inject enormous amounts of energy into the cluster. A GN activity is a sign that a black hole is actively growing. Every photon, every X-ray, every particle in a jet is evidence that Phoenix A is not just massive, it's alive. It's still pulling in matter, converting gravity into light and reshaping its cosmic neighborhood. This is what makes an AGN different from a dormant black hole. Dormant black holes may sit quietly for billions of years, but an AGN is the universe's version of a high-powered engine, and Phoenix A is running at full throttle. In the case of Phoenix A, the radiation we observe tells astronomers about the accretion rate, how much mass is falling in per year. With such an enormous black hole, even a small percentage of incoming gas produces energy billions of times greater than the total light output of the Milky Way. That's why Phoenix A's AGN is visible across such vast distances, and why it's a key tool for measuring the black hole's properties. By analysing the light from different parts of the spectrum, scientists can estimate the mass, spin, and feeding rate of the black hole. A GN activity can also be messy and unpredictable. The brightness can fluctuate, sometimes dramatically, depending on how much material is available to feed the black hole. In Phoenix A's case, the galaxy cluster provides a steady supply of gas, so the AGN likely remains active over long periods. But smaller inflows, star disruptions, or changes in magnetic fields could cause temporary flares or bursts of radiation. Observing these changes in real time helps astronomers understand how black holes like Phoenix A grow and interact with their environment. Relativistic jets, if present, would also be critical for understanding how Phoenix A affects its surroundings. These jets are not just visually spectacular, they are powerful conveyors of energy. They push gas away from the central galaxy, creating cavities in the cluster's hot gas and preventing it from cooling too quickly. In other words, the AGN's activity, including the radiation and possible jets, controls the balance of gas in the cluster, regulating both the black hole's growth and star formation in the surrounding galaxies. The AGN of Phoenix A may also produce spectacular radio emission. Observations of other ultramassive black holes show that jets can glow in radio frequencies for millions of light years. If Phoenix A has similar jets, its radio signature could stretch across the cluster, making it visible even to radio telescopes on Earth. This is part of what makes studying AGN so exciting. They are multi-wavelength phenomena, visible in X-ray, optical, infrared and radio, all at the same time. Phoenix A's AGN is an extreme version of what we see in other galaxies. Many galaxies have smaller, less active black holes, creating faint or moderate AGNs. Others are more powerful, but Phoenix A pushes everything we've observed to a new level. Its radiation, its feeding rate, its possible jets, all combine to make it a cosmic powerhouse, a galaxy whose very heart dominates its cluster. The physics behind AGNs is rooted in Einstein's theory of general relativity and the properties of gravity near black holes. Material falling into Phoenix A doesn't just accelerate, it stretches space and time itself. The high-speed motion in the accretion disk produces friction and heat, which turns gravitational energy into the brilliant light that we can detect billions of light years away. In simpler terms, Phoenix A turns matter into pure energy, shining far brighter than the billions of stars in its galaxy combined. Every photon escaping from the AGN carries information. Scientists study the shape, intensity, and timing of this light to learn about the black hole's mass, spin, and the environment around it. Even the presence or absence of jets gives clues about the magnetic fields and rotation of the black hole. For a black hole as extreme as Phoenix A, this is an unprecedented laboratory. We can study physics under conditions that cannot be replicated on Earth, where matter is crushed to unimaginable densities and energy flows at cosmic scales. Phoenix A's AGN also tells a story of cosmic history. Its activity shows that the black hole has been feeding for billions of years, growing steadily as the Phoenix cluster evolved. By studying its radiation, astronomers can trace back the growth history, seeing how matter flowed into the black hole, how mergers contributed, and how the AGN shaped its host galaxy and cluster. This makes Phoenix A not just a huge black hole, but a record keeper of the universe's extreme processes. Even though we can't see the black hole directly, its AGN acts like a spotlight in the darkness of the cosmos. X-rays from the accretion disk, radiation across the spectrum, and potential relativistic jets all tell us. Phoenix A is feeding, growing, and influencing everything around it. It's the ultimate example of how an active galactic nucleus works, amplified to a scale far beyond what we see in ordinary galaxies. When we talk about Phoenix A, we're not just talking about a massive black hole sitting quietly at the center of its galaxy. No, this black hole is the heart of an active galactic nucleus, or AGN, which is basically a galaxy's engine running on pure gravity. An AGN forms when matter, gas, dust, maybe even stray stars, falls toward a supermassive black hole. As this material spirals inward, it doesn't just disappear. It heats up, spins faster, and shines with enormous energy. This energy comes from the process of accretion, but on a scale that makes anything we see in the Milky Way look tiny. The infalling material releases radiation across the electromagnetic spectrum. That means X-rays, ultraviolet light, visible light, infrared, and even radio waves can all stream out from around the black hole. Observers on Earth can pick up this radiation with telescopes designed for these different wavelengths. And that's often how we first detect AGNs, a galaxy glowing far brighter than it should just from its stars alone. Phoenix A's AGN is powered by the infall of matter into a black hole hundreds of billions of times heavier than the Sun. Imagine the amount of energy released when that much gas, dust, and debris accelerates toward the black hole, heats up to millions of degrees, and emits radiation across space. The X-ray light from Phoenix A is so bright that it first caught the attention of astronomers using space-based telescopes. It's like a cosmic lighthouse, signaling the presence of an enormous feeding black hole in a galaxy cluster billions of light-years away. Some AGNs, especially the most powerful ones, can also produce relativistic jets. These are streams of particles launched outward from near the black hole at speeds close to the speed of light. They don't shoot from the event horizon itself, but from the region just outside it in the hot, spinning accretion disk, where magnetic fields twist and fling matter outward. If Phoenix A has these jets, and deep observations suggest it might, they would stretch for thousands, maybe even hundreds of thousands of light years, carrying energy far beyond the central galaxy and affecting the entire Phoenix cluster. These jets can heat the surrounding gas, suppress star formation in nearby galaxies, and inject enormous amounts of energy into the cluster. A GN activity is a sign that a black hole is actively growing. Every photon, every X-ray, every particle in a jet is evidence that Phoenix A is not just massive, it's alive. It's still pulling in matter, converting gravity into light, and reshaping its cosmic neighborhood. This is what makes an AGN different from a dormant black hole. Dormant black holes may sit quietly for billions of years, but an AGN is the universe's version of a high-powered engine, and Phoenix A is running at full throttle. In the case of Phoenix A, the radiation we observe tells astronomers about the accretion rate, how much mass is falling in per year. With such an enormous black hole, even a small percentage of incoming gas produces energy billions of times greater than the total light output of the Milky Way. That's why Phoenix A's AGN is visible across such vast distances, and why it's a key tool for measuring the black hole's properties. By analyzing the light from different parts of the spectrum, scientists can estimate the mass, spin, and feeding rate of the black hole. A GN activity can also be messy and unpredictable. The brightness can fluctuate, sometimes dramatically, depending on how much material is available to feed the black hole. In Phoenix A's case, the galaxy cluster provides a steady supply of gas, so the AGN likely remains active over long periods. But smaller inflows, star disruptions, or changes in magnetic fields could cause temporary flares or bursts of radiation. Observing these changes in real time helps astronomers understand how black holes like Phoenix A grow and interact with their environment. Relativistic jets, if present, would also be critical for understanding how Phoenix A affects its surroundings. These jets are not just visually spectacular, they are powerful conveyors of energy. They push gas away from the central galaxy, creating cavities in the cluster's hot gas and preventing it from cooling too quickly. In other words, the AGN's activity, including the radiation and possible jets, controls the balance of gas in the cluster, regulating both the black hole's growth and star formation in the surrounding galaxies. The AGN of Phoenix A may also produce spectacular radio emission. Observations of other ultramassive black holes show that jets can glow in radio frequencies for millions of light years. If Phoenix A has similar jets, its radio signature could stretch across the cluster, making it visible even to radio telescopes on Earth. This is part of what makes studying AGNs so exciting. They are multi-wavelength phenomena, visible in X-ray, optical, infrared, and radio, all at the same time. Phoenix A's AGN is an extreme version of what we see in other galaxies. Many galaxies have smaller, less active black holes, creating faint or moderate AGNs. Others are more powerful, but Phoenix A pushes everything we've observed to a new level. Its radiation, its feeding rate, its possible jets, all combine to make it a cosmic powerhouse, a galaxy whose very heart dominates its cluster. The physics behind AGNs is rooted in Einstein's theory of general relativity and the properties of gravity near black holes. Material falling into Phoenix A doesn't just accelerate, it stretches space and time itself. The high-speed motion in the accretion disk produces friction and heat, which turns gravitational energy into the brilliant light that we can detect billions of light years away. In simpler terms, Phoenix A turns matter into pure energy, shining far brighter than the billions of stars in its galaxy combined. Every photon escaping from the AGN carries information. Scientists study the shape, intensity, and timing of this light to learn about the black hole's mass, spin, and the environment around it. Even the presence or absence of jets gives clues about the magnetic fields and rotation of the black hole. For a black hole as extreme as Phoenix A, this is an unprecedented laboratory. We can study physics under conditions that cannot be replicated on Earth, where matter is crushed to unimaginable densities and energy flows at cosmic scales. Phoenix A's AGN also tells a story of cosmic history. Its activity shows that the black hole has been feeding for billions of years, growing steadily as the Phoenix cluster evolved. By studying its radiation, astronomers can trace back the growth history, seeing how matter flowed into the black hole, how mergers contributed, and how the AGN shaped its host galaxy and cluster. This makes Phoenix A not just a huge black hole, but a record keeper of the universe's extreme processes. Even though we can't see the black hole directly, its AGN acts like a spotlight in the darkness of the cosmos. X-rays from the accretion disk, radiation across the spectrum, and potential relativistic jets all tell us Phoenix A is feeding, growing, and influencing everything around it. It's the ultimate example of how an active galactic nucleus works, amplified to a scale far beyond what we see in ordinary galaxies. Extreme gravity close-up. As we move closer to Phoenix A, things start to get really extreme. This isn't the kind of extreme we can see on Earth, or even in the far reaches of the solar system. This is gravity at its most intense, a place where space and time themselves are warped. Near the event horizon, the invisible boundary around the black hole, physics behaves in ways that defy everyday intuition. Light doesn't travel straight, clocks don't tick normally, and the energy of radiation changes dramatically. First, let's talk about light bending. Normally, light travels in straight lines, and that's how we see the world around us. But near a black hole like Phoenix A, the gravitational pull is so strong that it actually curves the path of light. Photons, the particles of light, are forced to follow the curves of space-time created by the black hole's immense mass. This means that light from stars or gas behind the black hole can bend around it, sometimes making objects appear in places where they aren't, or creating multiple images of the same object. If you could watch it from a safe distance, you'd see a strange, distorted view of the galaxy, as though you were looking through a cosmic funhouse mirror. Then there is time dilation, one of the most mind-bending effects predicted by Einstein's theory of relativity. Time near the event horizon moves much more slowly compared to a distant observer. If you were to hover safely near Phoenix A's event horizon, something we can imagine but never actually do, you would experience seconds passing while hours, years, or even centuries fly by for someone far away. This is why black holes are sometimes called time machines in theory. Their intense gravity literally stretches the flow of time. For Phoenix A, with its massive size, this effect is even more extreme. The stronger the gravity, the slower time moves, and near an ultramassive black hole, the difference can be staggering. Next, consider redshift. Light escaping from near the event horizon loses energy because it has to climb out of the black hole's powerful gravitational field. This energy loss stretches the wavelength of the light, shifting it toward the red part of the spectrum, a phenomenon known as gravitational redshift. For astronomers, this redshift is a key clue. By measuring how much the light is stretched, scientists can determine the strength of gravity near the black hole, estimate the mass, and understand how fast matter is moving as it spirals inward. Observing these extreme effects requires sophisticated techniques. Scientists rely on spectroscopy, a method that splits light into its component colors or wavelengths. By analyzing these spectral lines, astronomers can see the fingerprints of elements in the accretion disk, measure their velocities, detect redshift, and understand the chemical and physical conditions of material near the black hole. Every spectral line provides a piece of the puzzle, revealing how matter behaves under the most extreme gravitational forces in the universe. X-ray studies are equally important. As matter accelerates toward Phoenix A and heats up in the accretion disk, it emits X-rays with energies far beyond what visible light can show. Space telescopes, like Chandra and XMM Newton, can detect these X-rays from billions of light years away. By studying the intensity, energy distribution, and variability of X-rays, scientists can map the behavior of gas near the event horizon, track accretion rates, and even infer the spin of the black hole. The combination of spectroscopy and X-ray observation gives an almost three-dimensional view of how matter behaves as it spirals into one of the largest black holes ever found. Another fascinating aspect of extreme gravity is the warping of space itself. Near Phoenix A, the fabric of space is stretched and bent so severely that straight lines are no longer straight, and the usual rules of geometry break down. Light from behind the black hole can circle around it one or more times before reaching us, creating arcs, rings, or even distorted images of the accretion disk. If we could photograph Phoenix A directly, we might see something like the photon ring predicted by theory, a bright circular outline where light has bent around the black hole multiple times before escaping. This is the same kind of effect captured in the historic image of M87's black hole, but on a scale far larger and more massive with Phoenix A. All of these extreme phenomena, light bending, time dilation, and redshift, are not just theoretical. They directly influence the signals astronomers receive. By carefully measuring how light and X-rays behave near the black hole, scientists can reconstruct its mass, size, spin, and the flow of matter around it, even though we can never approach it directly. The techniques are sophisticated, but the underlying concept is simple. Extreme gravity leaves fingerprints on everything around the black hole, and by reading those fingerprints, we can understand one of the universe's most powerful objects. Finally, considering Phoenix A's size, all of these effects are magnified. Its event horizon is hundreds of times wider than the orbit of Pluto, so the region of extreme gravity stretches far beyond what we typically imagine for black holes. The bending of light, the slowing of time, and the redshifting of radiation all operate over vast distances, giving astronomers a broad window into the physics of an ultramassive black hole. Every observation, from X-ray flares to spectral lines, is a clue to how matter and energy behave at the limits of space, time, and gravity. Environment and host galaxy. To understand Phoenix A, we can't just look at the black hole itself. We have to see it in the context of its home, the Phoenix cluster. This is not just any collection of galaxies. It's a massive cosmic metropolis containing hundreds of galaxies bound together by gravity, each moving through an ocean of hot, diffuse gas. The Phoenix cluster is one of the most luminous clusters we've ever observed in X-rays, which immediately signals that something extraordinary is happening at its core. At the center of this cluster sits the galaxy that hosts Phoenix A. This isn't an ordinary galaxy like our Milky Way. The central galaxy in the Phoenix cluster is a starburst galaxy, producing new stars at a pace far higher than the Milky Way. While our galaxy forms maybe 1 or 2 solar masses worth of stars per year, the central Phoenix galaxy is creating hundreds of solar masses of stars annually. This frenzied pace of star formation is unusual for a galaxy at the heart of a cluster, because the intense energy from the central black hole usually suppresses star formation by heating the surrounding gas. In Phoenix, however, both phenomena coexist. The black hole is actively feeding, while the galaxy churns out stars at an extraordinary rate. The environment of the Phoenix cluster plays a key role in this unique behavior. The cluster is filled with hot, ionized gas that radiates strongly in X-rays. This gas is not just sitting idly. It is slowly cooling and flowing toward the cluster's center, supplying fuel for both the black hole and star formation. This cooling flow is unusually strong in the Phoenix cluster, providing a nearly continuous stream of material. Without this abundance of gas, Phoenix A would not be able to grow into the ultramassive black hole we see today, and the central galaxy would be much less active. The central black hole exerts an enormous influence on its surroundings, a phenomenon known as cosmic feedback. As Phoenix A pulls in gas from its surroundings, it releases huge amounts of energy in the form of radiation, winds, and possibly relativistic jets. These outflows interact with the cluster's gas, injecting energy and heating it up. This feedback is essential because it prevents the surrounding gas from collapsing too quickly into stars, regulating star formation in a delicate balance. Unlike quieter black holes in more ordinary galaxies, Phoenix A is in a class of its own. Many black holes are relatively dormant, quietly sitting at the centers of galaxies with very little inflow of matter. These dormant black holes exert only a subtle influence on their environment. In contrast, Phoenix A is a powerhouse, continuously consuming gas and actively shaping the cluster around it. The feedback from this activity affects thousands of light years of surrounding gas, controlling how and where new stars form, and even influencing the orbits of nearby galaxies. The jets and outflows from Phoenix A, if present, would push gas outward at incredible speeds, carving cavities in the surrounding hot plasma. These jets are not just spectacular, they are essential for distributing energy throughout the cluster. By heating the gas, the jets prevent runaway cooling that would otherwise cause uncontrolled star formation. In this way, the black hole maintains a dynamic equilibrium, ensuring that the galaxy continues to produce stars at a high rate without exhausting all its fuel too quickly. The scale of Phoenix A's influence is almost unimaginable. The central galaxy dominates the Phoenix cluster in terms of mass and activity. Its gravitational pull organizes the orbits of other cluster galaxies, while its energetic output regulates the temperature and distribution of the cluster's hot gas. This combination of gravity and radiation turns the central galaxy and its black hole into the controlling engine of the cluster, a true cosmic centerpiece. The interaction between Phoenix A and its host galaxy is complex and ongoing. As gas flows toward the black hole, some of it is heated and expelled in outflows, while the rest feeds the accretion disk, powering the AGN. Meanwhile, other streams of gas cool enough to condense into stars, fueling the starburst activity. The result is a continuous cycle of feeding, radiation, and star formation, a cosmic ecosystem maintained by the black hole and the galaxy's gas reservoir. Spectroscopic observations reveal the motion and composition of gas in the central galaxy. By measuring shifts in spectral lines, astronomers can map how fast gas is moving, how it interacts with outflows from the black hole, and how stars are forming in different regions. These observations show that the galaxy is far from static. It is a turbulent, dynamic environment shaped by both gravity and energy feedback. X-ray observations provide additional insight. The cluster glows brightly in X-rays, highlighting the presence of vast amounts of hot gas. Observing these X-rays allows scientists to measure the density, temperature, and distribution of the gas, which in turn provides clues about how Phoenix A is feeding and how its energy output is distributed. The X-ray luminosity is so high that it initially drew attention to the Phoenix cluster as an unusual object in the sky, hinting at the extreme activity taking place at its core. One of the most remarkable aspects of the Phoenix cluster is how it contrasts with other galaxy clusters. In many clusters, the central black hole suppresses star formation almost entirely, leaving the galaxy red, dead, and quiet. In Phoenix, this is not the case. The black hole is active, but the cooling flow is strong enough to allow vigorous star formation to continue. This makes the Phoenix cluster a rare laboratory for studying how massive black holes and their host galaxies interact in extreme conditions. The feedback mechanisms at play are also a window into the life cycle of massive galaxies. Without feedback from the black hole, gas would cool too quickly, forming stars at a runaway pace and potentially exhausting the galaxy's fuel. Without the inflow of gas from the cluster, the black hole would starve and the galaxy would eventually quiet down. Phoenix A sits at the intersection of these processes, a balance between feeding and feedback that sustains both its growth and the galaxy's starburst activity. The central galaxy is enormous, far larger than the Milky Way. Its mass, combined with the ultramassive black hole at its core, makes it the dominant gravitational force in the cluster. Surrounding galaxies are influenced by this massive central galaxy, with their motions and interactions subtly guided by its presence. The galaxy's brightness, fueled by both old stars and new ones forming in the starburst, makes it a beacon within the cluster, easily observable even across billions of light years. Astronomers have observed signs of turbulence in the gas, likely caused by the black hole's outflows interacting with inflowing material. These turbulent motions help distribute energy, prevent runaway star formation, and maintain the dynamic balance of the cluster. The interplay between gravity, radiation, and gas dynamics creates a cosmic dance in which Phoenix A plays the starring role. Uncertainties in measurement. Measuring Phoenix A is not like measuring something with a ruler or a scale. You can't just stretch a tape from Earth to the black hole and count how many kilometers it spans. We are talking about an object billions of light years away, sitting in the heart of the Phoenix cluster, with a mass so enormous that even small errors in calculation can mean the difference between tens of billions and 100 billion times the mass of the Sun. The sheer size and distance make direct measurement impossible. Instead, astronomers rely on a variety of clever, indirect methods, each giving a piece of the puzzle. But even with the best tools, there are uncertainties. And Phoenix A pushes those limits like no other black hole in the universe. The first challenge is that Phoenix A is far away. Its light has travelled billions of years to reach Earth, and what we see is a snapshot of the past. By the time X-rays or visible light arrive at our telescopes, the conditions at the black hole may have changed. This delay means we are always interpreting history, not observing real-time events. When you combine this with the vast distances, even small miscalculations in light travel time, distance, or the properties of the Phoenix cluster can introduce significant uncertainty into mass estimates. One of the primary methods for estimating black hole mass is modelling the motion of surrounding stars and gas. In smaller galaxies, astronomers can track the orbit of individual stars near the black hole. Their speeds tell us how much gravity is acting on them, which in turn tells us the mass of the black hole at the centre. For Phoenix A, however, this approach is far more complex. Individual stars cannot be resolved at such distances, so scientists instead study the overall dynamics of the galaxy, how the stars in the central galaxy move collectively, and how the hot gas in the cluster responds to the black hole's gravity. These measurements require extremely precise instruments and detailed models, because the motions of stars and gas are influenced by many factors, not just the black hole. X-ray observations provide another essential clue. The black hole's active galactic nucleus shines in X-rays, and the intensity and spectrum of this radiation tell us about the accretion rate, how much material is falling in per year. The brighter the X-rays, the more matter is feeding the black hole, and the larger its mass must be to generate the observed energy. But this method is tricky. X-ray emission depends not only on mass, but also on the geometry of the accretion disk, the angle at which we view it, and the physics of the infalling gas itself. Small uncertainties in these factors can significantly affect mass estimates, making it challenging to pin down an exact number for Phoenix A. Another technique involves studying the hot gas in the Phoenix cluster. Clusters are filled with diffuse, X-ray emitting plasma that responds to the combined gravity of all the galaxies and dark matter in the cluster. By mapping the density, temperature, and motion of this gas, astronomers can model the gravitational forces at play and estimate the central black hole's mass. This method is particularly useful for ultramassive black holes like Phoenix A, where the influence of the black hole extends far beyond the central galaxy. Yet even here, uncertainties arise. Gas motions can be turbulent, affected by mergers, outflows, or feedback from the black hole itself. The hotter or more chaotic the gas, the harder it is to separate the black hole's influence from the surrounding cluster dynamics. Then there's the challenge of distance and cosmology. Phoenix A exists in a distant galaxy cluster, and accurately knowing the distance to the cluster is critical for calculating mass. If the distance is slightly overestimated or underestimated, it changes how we interpret the luminosity of the AGN, the motion of the gas, and ultimately the black hole's mass. Cosmological models have become very precise, but small errors can still amplify uncertainties when dealing with an object as extreme as Phoenix A. Even the concept of mass itself has limitations at these scales. For smaller black holes, mass estimates are usually straightforward. But when you're talking about tens of billions of solar masses, the surrounding environment becomes a major factor. The gravitational influence of the entire central galaxy, nearby satellite galaxies, and the cluster's dark matter halo all blend together. Disentangling the mass of Phoenix A from the mass of everything around it requires sophisticated models and assumptions, each introducing some level of uncertainty. Spectroscopy helps narrow the estimates. By splitting the light from the AGN into its component colours, scientists can detect Doppler shifts, showing how fast gas is moving toward or away from us. These velocities indicate the strength of the gravitational pull, giving another way to estimate the black hole's mass. But this technique is not perfect. Gas motion can be influenced by outflows, turbulence or past mergers, which can skew results if not properly accounted for. Phoenix A's environment is so extreme that modelling all these effects requires multiple layers of assumptions, each adding a potential source of error. Astronomers also look at the scaling relations between black holes and their host galaxies. In most galaxies, there's a rough correlation between the mass of the central black hole and the properties of the galaxy's bulge, its size, mass, and velocity dispersion. Applying these relations to Phoenix A gives a rough estimate of its mass. However, the central galaxy of the Phoenix cluster is unusual. It's undergoing a massive starburst, is fed by a dense cooling flow, and is at the heart of a huge galaxy cluster. These conditions are far from typical, making scaling relations less reliable and adding another layer of uncertainty. Then there is the matter of observational limits. Telescopes can only collect so much light, and for X-ray observations, signal-to-noise ratios matter a lot. Phoenix A is bright, but it is far away, and separating its signal from the surrounding cluster requires precise calibration and long observation times. Even small measurement errors in brightness, temperature, or spectral features can lead to differences of tens of billions of solar masses in estimated mass. One of the most fascinating aspects of measuring Phoenix A is that different methods sometimes give slightly different answers. X-ray modelling might suggest one number, galaxy dynamics another, and cluster gas observations yet another. Scientists then have to compare all these estimates, check their assumptions, and reconcile discrepancies. This is not a flaw, it's science in action. By using multiple methods and seeing where they converge, astronomers build a range of possible masses rather than a single, definitive value. For Phoenix A, this range is enormous by everyday standards, but it reflects the extreme scale and complexity of the black hole. Despite all these challenges, the evidence is clear. Phoenix A is far larger than anything in our Milky Way, and one of the most massive black holes ever discovered. But exactly how massive? Current estimates place it anywhere from tens of billions up to around 100 billion solar masses. That uncertainty is huge, but even the lower end of the range makes Phoenix A a true cosmic giant. It's not just a number, it's a reflection of the extreme physics at play, the dense environment of the Phoenix cluster, and the challenges astronomers face in studying the most massive objects in the universe. Even the event horizon size carries uncertainty. Because mass determines the Schwarzschild radius, a 10% uncertainty in mass translates directly into a 10% uncertainty in radius. For a black hole as enormous as Phoenix A, that could mean hundreds of millions of kilometers difference in the estimated size of the region from which nothing can escape. When we talk about the event horizon spanning the distance of the solar system or beyond, the uncertainty is significant but does not change the overwhelming fact. Phoenix A dominates its galaxy and cluster in every measurable way. Debates and alternatives. When it comes to the largest black holes in the universe, Phoenix A stands at the top of the conversation, but it hasn't been without debate. Measuring an object this massive and distant is extremely difficult, and different techniques sometimes give slightly different answers. Some studies suggest that the black hole might be somewhat smaller than the largest estimates, and this has led to lively discussion among astronomers. But even the lower estimates put it far above almost every other known black hole, making Phoenix A an extreme giant in the cosmos. The debate begins with the methods we use to measure black hole mass. As we've seen, Phoenix A is so far away that we cannot watch stars orbit it directly. Instead, we rely on indirect clues, the motion of stars in the host galaxy, the temperature and behavior of hot cluster gas, and the radiation coming from the black hole's accretion disk. Each method has its own strengths, but also its weaknesses. X-ray emission tells us about the material falling in, but assumptions must be made about the geometry and efficiency of the disk. Galaxy dynamics provide clues about gravitational influence, but the movement of stars can be affected by other factors, including past mergers, turbulence, or the surrounding cluster's gravity. Hot gas in the cluster adds yet another piece, but its motion can be influenced by jets, outflows, and other energetic processes. Because of these complexities, mass estimates for Phoenix A are not precise numbers, but ranges. Some studies place the mass at around 50 billion solar masses, while others push it closer to 100 billion solar masses. That isn't huge spread by human standards, but in cosmic terms, it reflects the reality of studying something so extreme. The debate among scientists is not about whether Phoenix A is big. It clearly is, but about exactly how big it is. This uncertainty is natural in astronomy, where distance, scale, and extreme physics make precision challenging. These debates also stem from the fact that Phoenix A exists in an unusual environment. Its host galaxy is at the center of a dense cluster with active cooling flows, starburst activity, and potential mergers with other galaxies. Each of these factors affects measurements. For instance, the inflow of gas from the cluster can make the black hole appear more active, which may lead to higher estimates of mass when using X-ray observations. At the same time, turbulence in the cluster's gas or overlapping gravitational effects from nearby galaxies can cause underestimates. Different research teams use slightly different models, assumptions, or observational datasets, which naturally leads to a range of results. Even when disagreements exist, all evidence points to Phoenix A being ultramassive, far beyond the size of ordinary supermassive black holes. This puts it in a class alongside a handful of extreme black holes that push the boundaries of what we understand about cosmic growth. To see just how extraordinary Phoenix A is, it helps to compare it to other contenders for the title of largest black hole. Take TON 618, for example. This is a distant quasar and one of the most famous ultramassive black holes known. TON 618 has been estimated to weigh around 66 billion solar masses, a staggering figure. Its mass was determined using a combination of spectroscopy and observations of the quasar's luminosity, providing a detailed look at the energy output of the accreting material. TON 618 is incredibly luminous, one of the brightest objects in the observable universe, but Phoenix A, while perhaps not quite as bright in quasar terms, sits in a galaxy cluster that gives it a different kind of power. It's not just about radiation, it's about the black hole's influence on its surroundings, and in that sense, Phoenix A dominates. Another contender is Holm 15A, a central galaxy in a nearby cluster that hosts a supermassive black hole estimated at around 40 billion solar masses. This black hole is not actively feeding at the same level as Phoenix A, and its environment is quieter. While Holm 15A's black hole is enormous, the surrounding galaxy shows less starburst activity, less hot gas accretion, and fewer signs of energetic outflows. By comparison, Phoenix A's combination of ultramassive size, active feeding, and energetic influence makes it unique. These comparisons highlight why astronomers continue to study Phoenix A closely. Even if some measurements suggest a lower mass, its environment, activity, and influence make it stand out among the largest black holes known. The debates about mass estimates are less about diminishing its significance and more about refining our understanding of the extreme physics at play. Every observation, every model, and every telescope brings scientists closer to a precise picture. But even with uncertainty, Phoenix A remains at the forefront of ultramassive black hole research. One reason estimates vary is the complexity of black hole growth. Black holes grow through accretion, mergers, with other black holes and the inflow of cluster gas. Each of these processes leaves a different signature in the observations. For example, if Phoenix A recently merged with another black hole, this could temporarily alter the velocities of stars and gas, leading to a mass estimate that is slightly higher or lower depending on the timing of the observation. Similarly, sudden bursts of accretion can brighten the AGN, which might make the black hole seem more massive if interpreted without accounting for variability. These dynamic processes add layers of uncertainty that scientists must untangle to refine mass measurements. Astronomers also debate the limits of black hole growth in the universe. Some models suggest that black holes cannot grow much beyond tens of billions of solar masses without exhausting their gas supply or destabilizing their host galaxies. Phoenix A challenges these assumptions, showing that under the right conditions, a dense cluster, continuous inflow of gas, and repeated mergers, a black hole can reach sizes previously thought improbable. This makes it not just a record holder, but a critical test of our understanding of cosmic evolution. The debate about Phoenix A also touches on observational technique. Different telescopes see different parts of the spectrum. X-ray observations highlight the hottest, most energetic material near the black hole. Optical and infrared telescopes reveal star formation, galaxy structure, and motions of cooler gas. Radio observations can detect jets and outflows. Each wavelength tells a different part of the story, and discrepancies between them can lead to different mass estimates. Combining these datasets into a coherent model is a challenge, but it's also how astronomers build confidence in their results. Even among the research community, comparisons are made cautiously. Some teams focus on luminosity-based models, which estimate mass from the energy output of the AGN. Others focus on dynamical models, which look at the motion of stars and gas. The choice of model, the assumptions about geometry, and the treatment of cluster dynamics all affect the result. This is why scientific papers often report a range of mass values rather than a single number, and why Phoenix A is described as possibly approaching 100 billion solar masses. Comparing Phoenix A to other black holes also highlights the diversity of ultramassive black holes. TUN 618, Holm 15A, and others represent different environments and growth histories. TUN 618 is a bright, distant quasar, shining across billions of light years. Holm 15A is a quieter, nearby giant, exerting influence on its local cluster without intense AGN activity. Phoenix A is unique because it combines ultramassive size with both a feeding black hole and a highly active starburst galaxy at the cluster's center. Its influence extends beyond the galaxy itself, regulating the cluster gas and shaping the evolution of surrounding galaxies. At extreme distances, small observational errors become significant. For example, an error in measuring gas velocities or X-ray brightness could translate to billions of solar masses difference in mass estimates. The same is true for assumptions about how efficiently matter is converted into radiation near the black hole. Scientists carefully calibrate their instruments, run simulations, and cross-check results to minimize these uncertainties. But some variation is inevitable. Even so, the conclusion is clear. Whether Phoenix A is 60 billion, 80 billion, or 100 billion solar masses, it is larger than almost anything else we know. It dwarfs Sagittarius A star, the Milky Way's central black hole, by tens of thousands of times, and it surpasses almost all previously known record holders. The debates about exact mass do not diminish its status as the largest known black hole in our galaxy cluster. What this means for cosmology. Phoenix A is not just an enormous black hole sitting quietly at the heart of a galaxy cluster. Its very existence challenges some of the most fundamental ideas in cosmology, forcing scientists to rethink how the larger structures in the universe form, grow, and interact. To understand why Phoenix A matters, we need to consider the theories of black hole formation. The first question is simple. How could such a massive black hole form? For most black holes, growth is a gradual process. Stellar mass black holes start as the remnants of massive stars, and supermassive black holes grow over billions of years by feeding on gas, dust, and merging with other black holes. But Phoenix A is in a different league entirely. Tens of billions of solar masses, far larger than almost any other known black hole. One possibility is that it began with a very large primordial seed in the early universe. Some theories suggest that regions of high density shortly after the Big Bang could collapse directly into massive black holes, skipping the normal star phase entirely. These seeds would provide a head start, allowing Phoenix A to reach its extreme size much faster than ordinary black holes. Another idea is repeated mergers. Over billions of years, galaxies in clusters collide and merge, bringing their central black holes with them. Each merger adds mass, and in dense clusters like Phoenix, this process can repeat many times. The central galaxy acts as a gravitational magnet, pulling in smaller galaxies and feeding its black hole with both stars and gas. This gradual accumulation, combined with the dense supply of cluster gas, could explain how Phoenix A grew to ultramassive proportions. Early universe conditions also likely played a role. In the first billion years after the Big Bang, gas was more abundant, denser, and cooler, which would have allowed black holes to feed rapidly without being limited by radiation pressure from the accretion disk. Phoenix A may have had a head start during this era, growing faster than black holes forming in more modern, gas-poor galaxies. Observing such ultramassive black holes gives cosmologists a glimpse into the conditions of the early universe, showing that the cosmos could assemble extreme structures earlier than previously thought. Phoenix A is also critical for understanding galaxy evolution. Black holes and their host galaxies evolved together in a process known as co-evolution. The energy output from a feeding black hole, radiation, outflows, and jets, regulates star formation in the surrounding galaxy and can even affect neighboring galaxies within a cluster. The sheer scale of Phoenix A amplifies these processes. Its activity affects hundreds of thousands of light-years of gas, influencing starburst activity in its host galaxy and controlling the cooling of the surrounding cluster gas. By studying Phoenix A, astronomers can observe co-evolution at an extreme level, providing data points far beyond what we see in smaller, more typical galaxies. These observations also raise the question, are there physical limits to black hole growth? In theory, black holes could continue growing as long as they have access to material. But in practice, several mechanisms can slow or stop growth. As matter falls in and radiates energy, the resulting radiation exerts pressure on incoming gas, pushing it away. Jets and outflows can also expel gas from the galaxy or cluster, starving the black hole temporarily. These feedback mechanisms act like cosmic regulators, preventing runaway growth. Phoenix A shows us that, while these limits exist, they can be overcome under the right conditions. A massive supply of gas, repeated mergers, and a dense cluster environment. Looking forward, future observations of Phoenix A could reveal even more about extreme black holes and the evolution of the universe. Next-generation X-ray telescopes will provide sharper images of the accretion disk and surrounding gas, while advanced radio arrays could map out jets and outflows in unprecedented detail. Gravitational wave observatories may one day detect the mergers of ultramassive black holes, giving direct insight into how Phoenix A and similar giants grow over cosmic time. Each new tool brings the promise of seeing the invisible, capturing energy and motion that today can only be inferred indirectly. Emerging questions remain. Could even larger black holes exist, lurking in other clusters or the distant universe? If so, what would their signatures look like? Would their event horizon span entire solar systems? How would their feeding processes differ from Phoenix A? These are not philosophical musings, but scientific challenges. By searching for extreme examples, we test our models, improve our instruments, and refine our understanding of the universe. Visually, returning to Phoenix A is breathtaking. Imagine zooming across billions of light years through the dense web of galaxies in the Phoenix cluster until you reach the central galaxy. The black hole sits at its heart, invisible yet exerting influence across tens of thousands of light years. Its gravity bends light, warps space, and controls the motion of gas and stars. Jets, if present, stream out at near light speed, sculpting the cluster environment. It is a cosmic engine of unimaginable power, a living laboratory where the physics of the extreme universe unfolds before our eyes. Phoenix A reminds us how much remains unknown. Each measurement contains uncertainties, each model relies on assumptions, and each observation raises new questions. We know it is enormous, active, and influential. But the details of its formation, growth, and ultimate limits are still being studied. For astronomers, Phoenix A is both a challenge and an opportunity, a chance to observe physics under conditions impossible to replicate on Earth and to understand the processes that shape the universe we see today. Its scale, mass, and activity are real, measurable, and extreme. The surrounding galaxy glows with newborn stars, jets carve through hot cluster gas, and X-rays stream out into space, carrying information across billions of light years to our telescopes. The universe is far stranger and more extreme than our everyday experience suggests.